I would say here that without any doubt, conservation of energy is the most important principle in all of science. So now we're going to talk about the principle of conservation of energy. The most important principle in all of science. And there's definitely multiple ways of actually saying this, but this is the important one. And so what is it that we're actually saying here? Well, what we know here is that this principle, what it does here is that it connects all forms of energy together. So conservation of energy connects all forms of energy together. So it's essentially a melting pot of energy, as we would say. Right? You could consider it in that language. So it's a melting pot of energy. And what I mean by melting here is that I can't tell the difference between potential energy, kinetic energy, and thermal energy. They're all have melted into the total energy of the system. So what you're seeing here is that the language here will completely remove work. The language here will completely remove the work. And remember, work is what? It's your intuition, right? That's how you think. Because everything that takes place in energy is not, it doesn't occur in the real physical space. It occurs in an abstract space called energy space. So the language here completely removes work, and we only focus on energies. We only focus on energies. So that being the case here, then let's write it up. Okay, so there's no more work. By the way, there is work. Anytime energy changes, that took work. Okay, here we go. So let's write down this principle of conservation of energy. There's two parts to this. It says that, you may have already heard this, it says that energy cannot be created or destroyed. Only transformed into different types. So what I'm really saying here is that we have this thing called total energy. And it really is this melting pot of all of the energies here. And this guy represents total energy. So when I have total energy, then what it means here is that it means something like this. I can take this energy and I can create kinetic energy, and then that kinetic energy can then create potential energy, and that potential energy can then create thermal energy. Or it could be the other way around. Maybe I create potential energy first, and then I go to kinetic, and then I go to thermal energy. So what you're finding here is that there's many iterations that could happen. This is this melting pot of energy here. And then this is the important point, or the key point of conservation of energy. And this is where the strength of the energy comes in. And what you find here is that the total amount of energy never, ever changes. And is a constant for a system. Okay, and it's a constant for a system. We show this in the conservation of energy equation. So when I look at the conservation, the total energy, that means here that I have something called the total energy. And this thing can never change. It's always a constant. And this constant says that it's kinetic plus potential plus thermal energy. This is the constant of a system. Once I isolate a system, it will always behave this way. But what you're going to find here is that many of the times we're not going to talk about total energy, but we're going to talk about total mechanical energy. So when I look at total mechanical energy, it's a sub-piece of this. And what you're going to find here is that total mechanical energy is also a constant, and it doesn't have friction. So you're going to see many of the examples that I'm going to do here are going to involve idealized situations of total mechanical energy. This is the famous principle right here. So this is what we're going to use for the rest of the semester. And it's going to come up a lot, just because the arguments for it are so strong. And they really simplify the picture of what we're looking at. So now I have conservation of energy. So now what I want to do, now is that I want to come in and I want to focus on its properties. Okay, it's its properties. And here we go. So we want to look at the properties of conservation of energy. Okay. So let's look at the first one. So the total energy is not what's important. So what I say here is that what's most important is that conservation of energy is a bookkeeping method for tracking energies. And how they transform. And you'll see what we mean by that in this very next piece here. So the key thing to note here is that it's the total energy is not important. It's this bookkeeping method that's important. And what we do here for tracking energies. And it's this tracking of the energy that makes it so powerful, especially when situations are really complicated. Now, let's develop this bookkeeping method a little bit better. Okay, so because the total energy is a constant, if one form of energy decreases, I could have said increases as well. If one form of energy decreases, another form must increase. So they're effectively inversely proportional to each other. Now, when you look at this thing, what ends up happening here is that we're writing a lot of words, but the power in conservation of energy, it's this visualization. We visualize this using energy bar diagrams. So you're going to see that you have a quiz next week and you have an exam next week. You are going to be asked to draw energy bar diagrams. So be prepared to actually use these things here. And they really make your world much nicer. So let me give you an example. Let's talk about total mechanical energy. Why am I doing that? Just because it's easy. It's easier to deal with 2 than to deal with 3. So we know that it's a constant. So what does that mean here? Well, I know that if I look at the kinetic plus the potential, these guys must be the same. Well, they're not, in this case, the way I drew them, they're the same. But now, if one energy decreases, okay, what energy is going to decrease? Let's say that I decrease kinetic energy. So if I decrease kinetic energy, then the potential energy must increase. We have no choice. And if one energy increases, then the other energy must decrease too. And one way to think about this is that you could, if we do an analogy here, we could imagine that the total is 100. And maybe we go, here, let me move this a little bit over. Apparently that didn't work. Let me try again. So when I look at this analogy, let's say that the total amount that I have is 100. And you have two hands where you're putting in money here. Well, if I have equal amount of money in each hand, then in this case here, it's got to be 50 plus 50. Now, if I decrease one of them, let's say I decrease to 25, well, the money didn't disappear. It's still in your hands. You just shuffled it. Then this must be 75. And if suddenly I increased the money in one hand, let's say to 80, then the other one has no choice but to be 20. So what we want to do here is that instead of dealing with numbers, we want to deal with bars. So here we go. So what I imagine here is that I have a total amount of energy here. And this then reads that this is the total energy that I could have. And what we know here is that this is the maximum energy that I can have. I can't have more and I can't have less. I can't create and I can't destroy energy. So it must be like this here. So then the question is, what does conservation of energy say in terms of the bars? So in this case, they got to be equal. So then the height of these bars have to be the same. So that's my kinetic energy. If I look at my potential energy, I draw my heights, and you could see that these guys are the same heights. But then I look at the next one here. You could see that the kinetic energy is a little bit smaller. So now I have a tiny bit of kinetic energy. So since this line here, right, this line means that it's a constant total energy, that means that I can't have less and I can't have more. So we have no choice but to say that this guy now has a larger potential energy. And then if I go the other way and go like, wait a minute, I know that my kinetic energy is now this big, then we have no choice but to now say that this guy has to be this big. And that's what this energy bar diagram really helps us to visualize this process. But wait a minute, what about the bookkeeping thing? Here's where the bookkeeping method kicks in. So what do I know here? Well, I know that if I have a little tiny kinetic energy versus a really large kinetic energy, right? So in this case, we know that this is a small kinetic energy, whereas this guy's now a large kinetic energy. It could only mean one thing. This means that the object must be what? Has a slow speed. This object has a fast speed. So if I'm talking about a car, we then will know that it's got to be moving like this. On the other hand, if we compare a small potential to a big potential, what do we know? Well, what we know here is that since potential energy is height, so this small potential energy then tells me that it must have what? A low height. Whereas this large potential energy tells us that it has to be a high height. So by looking at this bookkeeping method, we can tell when an object is either moving fast or it's moving slow here.